All right, so I intend this video to be about rules, just about rules for the definite integral. And I feel like that I don't know, I've been putting off doing a video about the rules just because it's rules. What can I say? It's not the thing that I get the most excited about to talk about. But anyway, so that's my intention. That's what I want to talk about and focus on in the video. But still, I think that as long as we're talking about this, I don't mind taking time to review some things, okay? Even if that's not what you aim to find in this video, if you just wanted to see problems that looked a certain way, then you'll find them. But because I can do whatever I want, I'm gonna start the video with a little bit of reviewing just because I want to keep emphasizing something, okay? So yes, I'm going to, because I can do what I want, I'm gonna review the definite integral for just a few minutes. I just feel better about doing that, and then we'll go on to the other thing that I want to talk about in the video. So here's the scenario with the definite integral. We can imagine that we're trying to find the area under a curve. Like maybe we're trying to find the area under a curve called f of x from point A to point B on the x-axis. Suppose that we want to do that, all right? Then what we had learned before, okay, that I'm reviewing now, is that we would have a partition which would break the space up from A to B into little blocks like x0, x1, x2, x3, x4. Okay, that takes you from A to B. And that blocks this off, and you get your rectangles that are just standing there in those positions. And then we get these things called sample points. The sample points tell you how tall each rectangle is going to be. So if like my first sample point is C1, if I go from C1 up to that y coordinate on the curve, then that's how tall this rectangle should be right there, okay? So you could think of it, and I know I've said it this way before, that the partition tells you the widths of the rectangle, and the sample points tell you the heights, all right? Okay, so then, okay, I gave that concept, I explained it, and we did a few problems, and the problems basically went like this. We did the Riemann sum, we did this, and we did this, and we did this. So what is all that stuff right there? This is the grand total, sum total, cumulative area of those four rectangles, okay? And in any one of these expressions, that first number, like say x2 minus x1, that's the width, like in specifically x2 minus x1, that's the width of the second rectangle from the left, this one right here, all right? And then f of c2, okay, that's this point, all right? Like if I put that number c2 into this curve, into that function, in that formula, I get the y coordinate on the curve. That's how tall this rectangle is. So that f of c2, that's the height of the rectangle, specifically the second rectangle from the left. Well, so if you added all that together, that would be a rough approximation to the area under the curve as pictured. It's not going to be perfect because the rectangles don't fit along the contour of the curve perfectly. So no, it's not going to be perfect, but it will be a rough approximation, okay? All right, now, so suppose that we want perfection, like what I've given you so far. This is not the perfect area under the curve, but we want things to be as perfect and as accurate as possible, all right? So how do we achieve perfection, or how do we get it perfect? That would be this next part, all right? The exact area under the curve, okay? Now, before I read you how I think we should look at that formula, here's the very first slide that I ever put up for this topic. I said, before we get into any math, how are we going to find the area of this shape? And I said, we can put rectangles around it, which is basically a Riemann sum. And we can find the area of each rectangle. We can add them together. That's what this is, all right? But then I said, well, the more rectangles you can fit in there, the more accurate your answer is going to be, okay? And you can see that by just noticing the difference in these pictures. This one those rectangles cover the area inside way better than these, okay? All right. Now, so this is the kind of thing that you might find in a calculus book. It will say the exact area under the curve is the limit as the norm of the partition goes to 0. What's the norm of the partition? It's the width of the widest rectangle. What happens as the widest rectangle, as its width goes to 0? Well, that's like going from here to here. Isn't the widest rectangle a lot smaller in this picture than it is in that one? Sure, definitely, okay? So all that, I mean, that might seem really deep, all right, and complicated. But all it's saying is if we go from here to here and beyond, we'll eventually get it perfect, all right? Okay, but nonetheless, this is just a Riemann sum. That will be the height of any one rectangle. This would be the width, all right? And that sum symbol means we're adding them all together. It's just in math notation, it's a way of saying that. Okay, now that would be perfect if you really could push the norm of the partition to 0, if you really could make the rectangles more and more numerous and smaller. You push that to its limit, you'll get the exact area. The definite integral also tells us the exact area, okay? So yes, we can do it this way. There is a way to do that. Yes, it's not easy, but the concept is what I want to emphasize here, all right? And this is one and the same thing. So those are two ways that we can give the exact area under a curve. And notice the mirroring of the notation. See that f, that function symbol? Well, that's like this. And see that delta x? Well, that's like the dx, all right? So that's why partially that's the reason behind the notation, okay? All right. So that is supposed to be a quick review just to remind you about that because it's complicated. So the more I remind you, the better I feel. So let's talk about the rules, okay? So what are the rules for evaluating definite integrals? Well, some of them are very straightforward, okay? You can break apart sums and differences, addition and subtraction, okay, just like this. So instead of doing the definite integral of f plus g or f minus g, we can just work on f and work on g, get those figured out, and then add or subtract their answers as needed. That one's not too bad. This one isn't either. Say that's a constant, k. You can bring that constant out. So it's like, okay, I can figure out this. What's the definite integral from a to b, f of x dx? I'll get that answer. I'll multiply it by k. So you can do that. This one is less intuitive, but sometimes we'll need to do this. It's called reversing the limits of integration. The definite integral from a to b, f of x dx is the negative of the definite integral from b to a. Well, what's the difference? The negative and the fact that the limits of integration are switched. Okay, that was a to b, this is b to a. Now, if you had some problem and you tried it this way and you tried it that way, you would find that they were equal. I'm not saying that that's mysterious or anything. If you did any problem that I've ever showed you in any video, this way versus that way, you'd get the same answer. But still, it's one of the rules, so I need to point it out. What if the limits of integration are the same? Well, no matter what the limits of integration are, if they are the same, no matter what they are, and no matter what that function is, then your definite integral will be 0, okay? So I guess you can think of it like this. This one has an intuitive basis to it. Say like this tells me the area under that curve from A to B. So, in other words, you're thinking like, well, there's point A, which is, I don't know, like say there's my curve, there's f of x, and here's point A, and then point B is somewhere else. And there's like a certain amount of area in there, okay? Well, what if like you said, what's the area from A to A? Well, that's like you've squeezed all the area out. A is here and B is over there. If your lower limit of integration is the same as your upper limit of integration, how could the answer be anything but 0? It'd have to be 0. Even if B was some microscopically number that's microscopically larger than A, there'd be a little bit of space between them, but if it's the same thing, the area has to be 0. All right. So there's a basis for that one. And this one also has an intuitive basis to it, but I'll just say that this one might be better to explain when we actually see a problem. All right. So I'll do a problem to explain this last one. But you could say that C is some intermediate place between A and B. So it's like you can go from A to C, and you can work that out, and then you can go from C to B. That would be the rest of the way, and work that out, and add them together. Okay. If I drew a little sketch to go with it, I think this one's real easy to understand. Maybe it's already easy for you to understand. I don't know. But I'll show you that one here in a minute. Okay. So let's just make sure that we can do this, and that's not so bad, you know. All right. So here's the style of the question. I don't want to tell you what the functions are that I'm working with, because I want to make sure that you can use the rules. Okay, if I told you the function, then that would give you a way to bypass the rules. And I just need to make sure that you learn them. So this says, well, the integral from -2 to 3, f of x dx is 4/3. And then the integral from -2 to 3, g of x. Now, g of x is some other function, and neither f nor g are given or known. But, all right, for g, it's -2/3. Can you tell me what this is? Well, didn't we just see a rule that said definite integrals can be split up over addition or subtraction? Right? So you can do it that way. And what does it amount to? Tell me the answer to this one, tell me the answer to that one, and subtract them. Right? That first rule, I said, well, that's not really that complicated of a rule. So what was the integral from -2 to 3 g of x dx? That was this one, so that's -2/3. Okay, and then I'm going to subtract. And what was the integral from -2 to 3 f of x dx? That was 4/3, so it would look like this. So I'm going to get -6/3 when I do the math there. -2/3 minus 4/3, and that's also known as -2. Okay, so there's that one. And you might say at this point, well, I was just talking to you about the area under a curve. How can the area under the curve be a negative number? Well, the area under the curve is not the only way to see this. I think it's the way to see it that's the easiest to understand, so that's what I usually talk about, but that is not the only thing that these can mean. We'll see some other applications later, all right? So that's a perfectly good and fine answer. All right, what about this one? What's the definite integral from 3 to -2 g of x dx? Well, that one's not up here. I got -2 to 3 g of x dx, but not 3 to -2. Notice how the limits of integration are switched. Well, wasn't there that rule that we just saw that said you can reverse the limits of integration, but it will be the negative of the answer you would have otherwise gotten. So in other words, the definite integral from 3 to -2 g of x dx is the negative of the definite integral from -2 to 3. That's how you can reverse the limits of integration. Why would I do that? Well, because I happen to have been given the answer to that one. That's why. I was given the answer to that one being -2/3. So it's negative, and then the answer to this is -2/3. Okay, so, well, that would be 2/3. All right, 2/3. Now, as I do this, I'd be worried somebody's reaction is, well, do we have to write all that down? I don't know. If you want to, you can. But if you understand that what that does, that I'm just going to take G and I'm going to subtract F, well, then just do that, all right? I'm not saying that you have to show the work. And same thing with this one. If you see this as just being the opposite of that because you know the rule, well, that's fine. Why would I want you to show the work on something that is really that simple? So do whatever you feel like you need to do. If you feel more comfortable writing the details, then go ahead and do that. All right, but I'm just saying, I don't think it would be necessary to do that once you understand it. What about this one? Okay, definite integral, -2 to 3, some constant k is 9/4 f of x dx. Okay, well, so I wrote it like this because I wanted to emphasize something about it. Right? For this particular video, this lesson, I'm just trying to emphasize that we learn and become familiar with the rules. Okay? So, all right, I wrote it like that because that's the way I wrote one of the rules on my other slide. And that rule said that, well, if this is a constant, then you can factor it out. Okay? So, in other words, your answer to this question is the number k times whatever the answer is to this integral. And I happen to be given the answer to that one. All right? So, okay, this would be the number k times 4/3. All right? And then if k is revealed to you, like if that's a constant, it really doesn't matter what it is. You can do this no matter what. And if you tell me, all right, I know that number, it's a 9/4. Okay, so I got 9/4 times 4/3. Okay, so that's going to be 3, right? The 4's will cancel. 3 into 9 is 3. Okay, right? So but the rule is there. I want to make the rule as apparent as I can. All right, so I think I did that. I wrote it just like I wrote the rule on my initial slide. What about this one? Well, I did say, and I even tried to give you an argument, I tried to convince you that if the lower limit of integration and the upper limit of integration are the same, no matter what they are, if they are the same, then the definite integral will be 0. Okay? All right, so that one is easy. Well, maybe they're all easy, okay? Just depends on how well you notice the pattern. All right, now let's do one more with one of the other rules. Okay, now, with this one, I think I'll do it 2 ways, just depending on the level of understanding that you need to have. All right? So, first way I'll do it, what should I call this? Method number 1. All right. First way I'll do this is I'll try to do it just by the rule, okay? So, let's see, this says for f of x, the definite integral from 2 to 7 is 9/2, but from 6 to 7, it's 1/2. What is it from 2 to 6? And you can see some similarity between these numbers, 2 and 2, and 6 and 6, and 7 and 7, right? But it's going to be this last one. So A to B. A is the beginning, B is the end. C is some point in the middle somewhere, right? This can be broken down into those. If you're okay with that, then do it that way, all right? So how would that give me a way to find this one? Well, okay, it would say the definite integral from 2 to 7 f of x dx, okay, is equal to, well, I see 6 as somewhere in the middle between 2 and 7. So we'll say 2 to 6 f of x dx plus 6 to 7 f of x dx. Wouldn't that be consistent with that rule that I just showed you? 2 to 7. 6 is some intermediate point between 2 and 7. 2 to 6 plus 6 to 7. So that takes you all the way. All right, from 2 to 7, if you stop at 6 and pick back up. Now, I'm looking for what? I'm looking for this one. So we got an equation here. I know that one. That one is 9/2. And I don't know this one, okay? But that's okay. I've got enough information to find it because I know that one right here. So now I just have an algebraic equation. 9/2 equals the thing I'm trying to find plus a half, right? So I'll subtract 1/2 from both sides. And I'll get this. The definite integral from 2 to 6 f of x dx is equal to 9 over 2 minus 1 over 2. Okay, so 9 over 2, that's 8 over 2, and that's also known as 4. So that was 4 all along then, okay? All right, now that's the first method, which might be okay with that. I always say maybe that's good enough, but I want to give a little more insight into this, all right? So it's like this. I'll give you some more insight into why that works like it does, and also emphasize some other things that I've been telling you about in some of the other videos. So say that, now this is a little bit hypothetical, but it's all consistent with everything I told you. I don't know what f of x is. It's not given. It doesn't tell me what that function is. The equation's not given. Really no useful information about it is given. But it is a function, all right? So let's say that it's a function which I just, in completely generic terms, draw like that. I happen to know that if I wanted to think of this for the time being as the area under the curve, I happen to know that if you go from 2 to 7 on the x-axis, then that area in there is 9 over 2 square units, all right? I put u square. I'm just trying to say something like 9 over 2 square feet, or like whatever the units are, but that's an area measurement. So this area, that's 9 over 2 square units. That's this. That's the definite integral from 2 to 7. I know from 6 to 7, the area under the curve is a half. So it's like I know that this part right here, like say that's 6, okay? That is 1/2. Now then, in that way then, I could say this, what this last rule really says is that the whole is the sum of the parts, okay? So if that entire area is 9 over 2 square units, and this little piece here is 1 over 2 square units, well, how much space is over there? Well, the whole is the sum of the parts, okay? Well, so this would be 4 square units, because 4 plus a half is 9 over 2. 9 over 2 is 4.5. All right, so that's another way I could do it. And that gives you a little bit of insight to the rule. I don't want to just write the rule down and just go over them like they're nothing. I think it's better if I give insight where I can. Sometimes the insight makes it way more complicated, but not in this case. All right. Okay, so it's like I see, well, that's the whole thing. That's a little piece of it. This is the rest of it. That's another way that I could see this one. All right, now, it's like a lot of things in math are like that. Maybe when you first see that, it just doesn't dawn on you that that's what it means. But, you know, as you study math on your own more and more, as you go through your degree or whatever it is you're doing, you might try to realize things like this on your own. They're true in places that you might not expect.